Things are just getting a little hairy with the setup this morning, this afternoon, this evening, whatever time it is. I don't even know anymore. I almost forgot it was Tuesday. So we're just getting started here. We're going to just get set up and get everything going. So don't mind me for a moment. So how's your week been? Yeah. Had a pretty busy day. Pretty busy weekend. School's just getting started over here where I am right now, the kids. And, you know, going back to school in this situation that we're in right now, the pandemic and everything, it's not easy, I tell you. We have this, so our school board for our kids is allowing everyone to have like remote learning. And that means kids working from home, kind of like I am right now. And we decided to opt for that instead of going back into school because we felt like the plan here in Little Ontario, Canada is, not awesome. And so we were playing it safe. And a lot of the guidelines and the messaging around the whole thing was, hey, let's keep the kids home so that the kids who do need to go into school for whatever reason can have a safe return in the fall. And so we said, yeah, let's do that. We're able to. Man, it's not going well. So they tried to set everything up, right, and get things going. But those poor IT people that are doing the setup, man, I would not want to be them right now, because they're stuck. They were supposed to start on Tuesday. Well, Tuesday we had a blackout across the city. So like, okay, well, I guess we'll start Wednesday. Wednesday comes and they're probably so swamped trying to set everything up at the last minute because, again, government never really had a good plan to begin with. And you know what technology and computers are. So they said, okay, well, we're not done today. We're going to get you started tomorrow. So it's like, man, I don't know what's going on right now. And so here we are, trying to enjoy a little bit of programming. Try to enjoy a little Haskell in what little time we have in our spare time. So thanks for coming by, hanging out with me. Today's a rough day, I'm not going to lie. I am not having a good moment right now, and I don't know if some of you go through this too, but I have these days where it just kind of hits me, and I'm like, you know what? Maybe I don't know really anything about this business of programming. Now, I've been doing this a long time. Right? I'm not a young person, kind of in the middle of young and old. Right, I'm going to be hitting my 40s in a couple of years. And and I've been programming since I was a kid, pretty much, in various languages. And I don't know if it's just the pandemic or it's just my situation right now and things I've been through, but I get these like days where I'm like, maybe I've just been like BSing my way through this whole programming business. And there's a lot of people out there. I get this, a lot when there's people out there that are, really super good and they're like really flexing their stuff. And I'm just in awe of the things they can do, right? And I think, wow, that's amazing. And then a little voice in me is like, man, you're not like that. You're not great or whatever. Some days you don't even know what you're doing, literally. So I guess the question is, sometimes we're kind of getting these things is, how do we deal with those kinds of feelings when they strike with us, and what do we do about it? All right, so I don't know. Me, sometimes I just dig in harder and I work on hard stuff, like I'm doing right now with this project. And I say, you know what? Maybe I'm just in a rut. Maybe I'm just bored. Let's just try something I haven't done before. Let's make a database. Other times I'm like, you know what? I need to take it easy on myself. Let's just do something boring and simple that we know how to do. Just to remind us that we still know kind of what we're doing. But how do you deal with it? I don't know. I'm always kind of curious because I'm not sure this is... I know people talk about this stuff. Yeah, but I also know that sometimes you don't want to talk about this stuff because professional reputations being what they are. So how do you deal? It's cool on the stream. If you just want to chat at me sometime, that's cool too. You can send me a DM on Twitter at Agent Ultra. You can hit me up on the FP chat on Slack. But I'm curious. I'm curious to know. So it can't be the only one, right? This can only be temporary, like most things are. So tonight, we'll see how far we get. Last week, where were we? We were building a bee tree. And kind of struggling on the bee tree, to be honest. And to be frank too, I meant to kind of follow up on the things that I was getting stuck on during the week, but I just haven't had time. Again, this whole school thing with projects that I'm working on at work, pretty stressful. Just trying to keep my head above the water, so to speak. So, but I did have a thought about it, at least the other night. I was trying to go to sleep, and we were working on the insert part, and we were going on this idea of like, okay, do I pull out the middle key that I looked for and put that in the parent, and then split the left and right sides of the leaf that I'm looking at when we're building a node? Or would that break the invariant for nodes? All right, so the invariant for these things are like super important. It's kind of what makes them a B+ tree, right? And the invariant for a node, right, is that, maybe we can put this in the comments to remind ourselves. So the invariant of a node, there's a few, and there's some exceptions, which makes it kind of, oof. They can't have less than order 5 by 2 elements or children. I think it is. So what that means is that if we're splitting the leaf to making a node, I think that means we have to have enough kids in the node to keep this invariant true. The only exception to this is when a node is the root. We can have at least 2 as the minimum. Yeah, at least 2 children. All right, so if we're going for just 3 elements, all right, we go to insert 9. All right, that starts off our tree at 9 with just the leaf as the root, which is allowed. That's the only exception. The leaf can be the root, otherwise it's always at the bottom of the tree. When we have inserting a 10, right, and say our order is 3, I think, and we can put the 10 in. But if we go to insert another one, we can't. Leaves have to have the order -1 number of keys, so we need to split. That's what we do here, right? Yeah. So if they're not less than order, that means we're doing this branch here. So that's when we got to split into the node. When we go to say 11. So what I think we need to do when we split the leaf down here is that we take the 9 on the left side, because we check the 10. 11 is greater than 10, so we're going to insert that on the right side. 10 is going to become a key in the node, and the node will have 2 children. The left side, the left leaf, which will be the leftmost leaf, which will be the 9, which will contain the 9, and then the rightmost leaf, which will contain the 10 as well, and the 11. I think that's how we want to go. So let's give it a shot. Okay. So what do we need in order to start this equation? We need the left values, the middle key. So let's start let binding some things. We don't really need to. We can maybe jigger things around. I just want to bring into scope the values we're going to need to make this happen. Oh wait, sorry. We're not doing that here. Sorry, we're doing that as split leaf. Excuse me. Or we have some things already. Okay. Let's see. That's the left keys, right keys. We split at the mid. This is if the key is less than our order on the leaf. So we're okay to insert. We still had a hole here. I'm not sure if this makes any sense at the moment. We just want to split the leaf here. Something else is going to determine if we need to split a leaf. Okay, right, okay, so when we are doing that, we're saying if the key is less than the midpoint value in our keys of this leaf, yeah, we're going to insert on the left values. Oh, we're going to be constructing a node. That's right, okay. All right, so we split those out. Left keys, right keys. Split at the midpoint. Left values, right values. Split at that, the midpoint as well. Can even create a little binding for that. Oh, well, I guess it's not that important, but. I see why. Yeah, never mind. Doop, 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 doop. Right. So then we take the left key prime, left values prime. We still have to define insert into to do that. The left side and the right side. Okay, and the left side will point to the right. Tie the knot there, and we construct the node from that. Okay, we just need to figure out what the keys are going to be for the node. That's right. And then, so that should be the midpoint value, which I think, as I recall, is what the v.splitout will make head of the right if there's values there. So if our order is greater than whatever. Let's just double check that. Pretty sure that's how split out will work. So I just want to make sure that when if our order is relatively small, we call split at, say 1 element, are we going to get an empty list for left and then 1 element on the right? Or are we going to get 1 element on the left and empty list on the right? Which side does it prefer? Not 100% sure I know that off the top of my head. I could also just be super tired right now, and maybe I do know the answer, but I'm going to just pull it up in a REPL because I can. Might as well just be sure. Actually, I probably should. Whatever. Qualified. Split at. Say our midpoint is 1. From list. Okay, so it's going to do that unless we end up with 0 as our midpoint. And that's going to be the right side. It's going to get it. So as long we're going, I believe the midpoint formula is here. We're taking the ceiling of our division divided by 2. So that means that we're going to get, in the case of a list of 1, we're going to get split at 1. Like, so we're going to get 0.5, we're going to take the ceiling of that. So we're going to end up with that in our small case when we try to split this leaf. I think the small case, it depends probably on whether what we're trying to insert is greater than or less than 1. Because that's going to be index 0, isn't it? Oh, you know what? Just put the parentheses in, Jim. It's all good. Right, that's going to throw an exception because we're out of bounds now. Yeah. So our small case might actually be a bit of an issue. Can we even have a B+ tree that is order 1? Do we even have to worry about this? Good to know. Let's find out. What's the minimum order? Minimum degree. Sometimes called degree as well. Yeah, okay, it has to be greater than 2. That makes sense. There's some more invariants we need to uphold. Yeah, so we can't even have anything less than that, so that's good. That means that Basically, our example here is we don't need to worry about it because our degree 2, if we divide that in half and take the ceiling of it, it's always going to be 1 at least. Which means we're going to get this, or if we only have one key, we're going to get, oh yeah, that's right, still that. Right, degree 2 divided by 1, yeah. But we could still, and we'd have t minus 1 less keys, yeah, so we could have this case here. Okay, it's good to know. Whew. All right. Good times. Let's just make sure we document that again. Degree of a B plus tree. Greater than or equal to 2. Cool. So you know what? I'm going to let that simmer for a minute. Get back to it in a second. I just want to make sure that when we're constructing our tree that we have this greater than or equal to 2. And maybe we can enforce that invariant a little bit in our types. Why not do that? So let's create a new type, degree of the tree, which will be an int. We'll derive some basic stuff. We could even derive none. Yeah, int. That's right. IDE, don't fail me now. Add deriving strategies, please. There we go. Add driving via, please. There you go. And that just allows us, for all intents and purposes, to treat this as a derive the num class. So we could treat it as a number, since it essentially is. But we're going to have to give ourselves a smart constructor for this type. You give me an int, I'll give you a degree. No matter what int you give me, though, if you give me something less than 2, we're just going to give a degree of 2. That covers all our bases. We don't even need it with guards. We can probably write it even shorter than that. Excuse me. If. I mean, that's not the worst. This is pretty clear too. Right? It's all right. Don't need to get too fancy here. Little guard. I like using guards for smart constructors. It just seems nice. Almost like what they're for. Okay, so our minimum degree there is 2. So as long as we're using this function to construct degrees, then we're always going to get a correct one. Then we can go ahead and replace this with a degree. Replace that with a degree. And actually, we call these orders, the order of the tree. Call that order. Oh, we've got a couple cases here. And, oh, forgot one there too. Cool. Super duper. Okay, we're going to get a bunch of type errors in this stuff here because we just changed the type of that. And we'll need to unpack the order for a degree constructor. And change that to degree. Or, no, you can give us an int. That's fine. We'll just wrap it. Oh, now that it's a function. That's going to be annoying, isn't it? Naming things. Maybe degree is better. But then we're going to have the same problem if we end up calling this degree as well. This little fun one here. So, ugh. Let's stick a little prefix on there, I guess. Kind of a common thing you see in some circles in Haskell. I'm not a huge fan, but it works. So in this case here, we do need to pattern match out the actual integer value, I think. Oh, getting a raid. Welcome, raid. Hey, Bivich. Chiroptical. How's it going, everybody? Thanks for coming and joining my stream, checking it out. We're knee deep in some data structure work right now for the DataStore. We're trying to build a B+ tree. How to pronounce it? Chiroptical. Okay. Thank you. Apologize for butchering that a little bit there. Yeah, so we're building a B+ tree, at least trying to. It's kind of like my first go around at building a B+ tree in I think ever, and certainly in Haskell. Oh, thank you. Doing my best. And yeah. So we're just creating a little smart constructor because we're talking B+ trees have orders or degrees. So just fixing that right now. And just making sure that just with a little bit of new type safety that we can enforce our invariant, that our degree of our tree is greater than or equal to 2. Right. So we have to wrap those in muck orders, make orders. I think that's where the MK comes from. So if you're not an English speaker and that shortening doesn't make sense to you, or at least you're not a native English speaker, that MK doesn't make sense to you, that's I think what it means, make. Whenever I hear Simon Peyton Jones, because he uses this pattern too a fair bit in some of his code, he says muck. This makes me laugh a little bit inside. Muck order. I'm not going to try and do his accent because it's brilliant and wonderful, and I would butcher it horribly. Okay. Right, so we're splitting a leaf right now because when we go to split, handle this case where we have too many dang keys in our leaf. We need to split it out. Create a node with 2 leaves. Muck Ultra. That's right. MK Ultra. Oh, isn't that a mind control program? Ah, dude. Oh, that's cool. Maybe that's where it comes from. Haskell is taking over our minds. It's a CIA experiment. I knew it! This is why I can't stop thinking about it all the time. And why I've been ruined in other programming languages. Am I avoiding the question? So somebody asked, the U.S. government psychedelic drug experimentation program. Like, where does my name come from? Agent Ultra doesn't come from this program, unfortunately. It's another program. I'm not allowed to talk about it, though. I'm with this program, though, for sure. Maybe not. But maybe I am. Okay. Yeah. B plus trees. Splitting the tree. So, again, I am totally open. If anybody wants to shout out anything about the code, ask questions, feel free to stop me. This is a pretty chill stream. I am obviously not trying to teach how to do this properly. I'm learning myself, and other people are learning as well. So feel free to ask questions if you don't know what I'm doing, or if you want to know more about what I'm doing. Or if you think I'm missing something and want to lead me in the right direction, I could use the help too. Right, okay, so we need to remember, we need to fill in this hole for the formula when we're constructing, or the equation when we're constructing this node here. We have the order, and assuming we have an equation for insert into, we're inserting the value into our keys. At least in this case, on the left side. And so we need to know what to do. We need to know what keys to bring into the node. Now our invariant on nodes is a little important. They have to have at least a minimum of order divided by 2. The ceiling order divided by 2 of children. So I guess keys, it doesn't really, there's no limit on that as long as it's order -1, less than order -1. I'm just going to double check that if this has it in there. Yeah. This is a B tree. B plus tree. Google's not liking the B and the plus, I guess. Oh, I am in that channel myself as well. We might do some pair programming or streaming together at some point, maybe. Might do a little bit of pair programming or streaming with Vlad. It seems like I've sort of kicked off a bunch of, I kind of kicked off my stream around the same time with a bunch of other people who were thinking about kicking off their streams. And we're all doing Haskell together. And we thought, or Vlad came up with a great idea that to spread the love and joy that is Haskell, that we should do some streams together. So he had Sandy on for his podcast Sundays about a week ago, I guess, or so. that was a great episode. I thought that was pretty awesome. That stream was amazing. And yeah, Chris Penner on. Chris does, he wrote a book called On Haskell Optics. I forget what it's called exactly, but it's pretty hard to miss. And Sandy wrote recently a book on algebra-driven development, which I've been enjoying quite a bit. Those of you just dropping in, Optics by Example, that's the one. If you've read Algebra-Driven Development, or if you've finished it already, let me know what you think in the chat. I'm kind of in the middle of it. I'm rereading, actually, the first third of it that I kind of like whipped through. Kind of curious. It goes a lot to me of a lot of the things. Yeah, it is really good. That Conal Elliott has been saying, like his denotational design talks. Of course, things from other books like that I've read over the years, SICP and things like that. And it's a really interesting approach. It's really cool, and it's something I haven't really encountered outside of the Haskell sphere, which is kind of interesting. I was talking with a friend of mine, and I was having a hard time doing LeetCode exercises, and I was just pounding the LeetCode exercises. Just wanted to, get down on my data structures and just stay sharp. I don't push myself too hard on it, but I was having a tough time with it. I felt like, I'm not going fast enough on these, or it's taking me a really long time to solve some of them. For somebody who's been programming so long and all this stuff, I felt like I should be better at it. And he had a good point. He's like, you know what? You're thinking algebraically these days, or you're trying to warp your brain to think algebraically. And for a lot of algorithms problems, you got to think sometimes logically in terms of invariance, like we're doing right now. So it's definitely an interesting mental model, and really, really worth reading, because the prose is really good, and the examples are pretty interesting. Really, so I don't know. I've also been playing around with trying to redo some of the examples in a theorem prover. So using lean to see if you can get the machine to help you check a little more, because I saw the Haskell code for it, and it's good, it's cool, but yeah, I was just wondering if there's other ways to approach it as well, because I'm just so enamored with the idea. All right, so the other thing too is I just want to get used to thinking that way and doing thinking that way, which is a lot different than thinking about thinking that way. I think I'm self-taught for all my programming career. And my recreational mathematics, I would say. I'm not a mathematician by any means. The one thing that really helped me break through when I was starting out and rediscovering math, that I really enjoyed it recreationally, was doing the exercises, doing the proofs, and proving it to yourself, and just not being afraid of just asking weird questions and getting help. Who cares if people think you're dumb? They're worse for thinking you're dumb for asking questions and wanting to enjoy math, so don't worry about it. Ask away. Right, B plus trees. So let's just look up, I wanted to look up, not search, we know, well, sorry, no search, insertion. Yeah. What bucket? Such terminology. The book is not full. Right. Gotta split the buckets. What we're working on right now. So the original node has the ceiling of L plus 1. Oh no. Wikipedia notation. Leaf? Yes. Properties. algebraic properties and other properties are also good to discover. And in fact, maybe that's what I'm missing in this whole exercise of trying to develop this B+ tree. Is that we're not, we should probably be starting with the properties and encoding those in tests. But again, it's a different way of thinking, and when it comes to like data structures like this, I kind of just try and make something first and then write a few tests and show that I've done it wrong and then fix it. I don't know if that's the best approach though. Kind of make it work. That's what I try to do. Okay, so the original node, I guess, has half the items. The new node has half the items. Okay, the new node has the half the items. So we move this one up to the parent. Insert the new node to the parent. Ooh. This last step is the part that's going to like twist me inside out, I think. Constructing trees downwards is really easy. You know, sometimes when I'm afraid of doing stuff in Haskell, like I'm like, oh, this sounds really hard. My brain just goes back to like pointers and C, and I'm like, this should be easy. But this one might be a little bit tricky in that part. Right. So this has to take the L plus the ceiling of the lower half of from the original node. So the leaf node. And then the new leaf node gets the other half, I guess. That's probably it right there, isn't it? This has to take... How do we want to do that? Express that in this equation. Basically, something like the lower half. It's kind of what I want. I don't know what that is yet. But it's gonna have to be of the type vector of k to be correct. Yeah, Chris Okasaki's book, Functional Data Structures, was really, really eye-opening for me. That would be really cool, Corruptical. That would be very cool. If you're going to blog it or write about it or stream it, let us know, because I think that would be very fun to follow. Yeah, pure functional data structures. That's what really got me over the hump of worrying about Haskell performance as well. I mean, you still have to worry about performance, but not as I don't worry about it that much. Unless I need to worry about it that much, then I do, which we might on this stream. I don't know how deep we're going to get into this this project, but we'll see. Okay, so I want lower half of something, and then in the child leaf. We're going to construct a node. We actually don't. I don't think we actually need to split the leaves here into left and right. If I'm reading this right. right? We move these into the parent. So that comes into the node's children's vector. And then we construct a new leaf with these elements underneath it. And then I guess if we break the invariant again, when we're constructing this node, we have to like recursively go to that node's parent and move things around. But yeah, hopefully it all pans out in our algorithm and things will be good. Go. Right, so we don't insert into, yeah, we don't need to split at the midpoint. Well, we need to split at the midpoint. Pardon, that's right. We just don't need this down here. So left, I guess left is actually the, I don't know if that's the right name for it now, because this doesn't really tell me all that much about what this means when we split the bucket, so to speak. I wonder if there's like a better example. Oh, at least it has all these, the invariants kind of spelled out here. It's good to note. So before inserting the new record. Okay. So we do this split, and then we keep splitting until we can't split anymore. And then we insert our value, and hopefully it'll have a place to go where the invariants will be violated again. So I guess just indiscriminately I split those. Doesn't really matter. Yeah, well, I mean, it's hard. Even if you didn't go to university, it's pretty hard. So no worries. They're cool. They're definitely cool. I don't know. Maybe. Data structures in C. See, I have a problem, right? Like C is the language I grew up with. Pretty much. I mean, I really started with BASIC, to be frank. I was like just a kid filling out, you know, little Byte Compute magazine game listings to age myself here. And I don't think I really knew anything about what I was really doing in C. I was kind of just following along with this guide I got at one point in time. That was like this little thick book that was like how to program games in C. So I just kind of like followed along and copied and imped things and just kind of tweaked it as I needed to. C was very forgiving in that respect. And yeah, so I don't know. Every time I want to also check out, there's a cool book that recently came out that looked interesting. It was David Bird. Algorithm design. Richard Bird. David Bird. Richard Bird. I think he wrote some other books on Haskell, if I'm not mistaken. This one's pretty new. I think, yeah, this is the one I'm thinking of. Should be pretty new. So that's the Okasaki book, Purely Functional Data Structures. Algorithm design with Haskell is I find a little bit different. You have to think a little bit differently. Whereas if we were doing B+ trees in C, I don't want to say this would be easier, but it would be easier for me to do because I'm more familiar with it, if you know what I mean. But what's surprising sometimes about Haskell is that And what really hooked me on it was just that how some things that seemed like, oh, that's going to be pretty tricky to do. And I would just code it up in Haskell, and it was actually, the program was a lot shorter than I expected it a lot of the time. Yeah, Cambridge Press, pretty pricey, but you know, if it's a good book, it's a good book, right? So probably totally worth it. He's written some other stuff. Yeah, thinking functionally in Haskell, which I haven't gotten too deep into, but I have skimmed a little bit. And he has a pretty unique way of, pretty unique style in that book. He really goes hard on the composition and thinking in terms of on composition. It's really a really interesting book. I like that one a lot. I should finish that one off. There's so many Haskell books to read. So little time. Yeah. So I guess left here is like our lower half. Right, to follow this, or maybe it's the upper half. Yeah, because that's ceiling and bottom, floor. I don't quite understand where this L is coming from, or what that means. Let's find another. There's also a good description of this in The Art of Computer Programming, but it's not very easy to share on the stream. If you're looking for a really good, thorough description of B trees and B plus trees, I highly recommend that one if you have access to The Art of Computer Programming. But again, the design of that algorithm assumes you have pointers and can mutate things. Let's try Geeks for Geeks again. Sometimes the notation is like, digga. Nope, terrible. Oh, this is neat. I like little visual tools. Right. That's about what I would expect, yeah. 5, right? And then, let's say 34. I think this will, since we're degree 4, this one should insert there as well and split. Ah, see, we only kept one key there. Okay. But we have the 2 children. 3, 4, 5, 3, 4. Okay, cool. I am on the right track. Visual tools do help. Great. Yes. This is about what I'm expecting. Okay, cool. So we do split them into 2 halves. And the relationship here, this between the 5 and the 5, is kind of the other thing I was investigating at the beginning of the stream when we were looking at v.split at. So our min, it doesn't let us do min degree of 2 here. Let's try one with 3. All right, so we insert there. That's 4. Again, it should be on the same level, so this is still a leaf node here. 3, this will split. Okay. So see how we only have 3, but we have 2 elements on the right-hand side. So we're kind of, and we have the 4 here. That's what we need to make sure of when we're doing the small cases. That we do that. So I guess that does mean that no matter what degree we have, we should have when we do this initial split at least, We should have that for, and that kind of relationship. The head of this vector is going to be in the parent node there. I think that might be a thing that might be true. Maybe. Let's keep going with this one though. Let's try inserting again. Bunch of values. We're going to split again. Right. That splits. Let's try inserting 6 again here. That's got to go there. And that's where we did the recursive insert into the parent. Deletions, a little bit different. So we will have to support deletions in this because we're going to support our key database is going to support. So I think we have the 3 commands, right? Set, get, and delete. All right, so it's going to go to the 4 and just remove it, and and rebalance everything. So deletion is pretty tricky. Because those invariants on this tree have to hold at all times. Cannot be violated. The guarantee is that if you hold all of those invariants on this tree will always be balanced. So whenever you have that kind of like always be balanced thing, deletion is going to be a pain in the butt. Insertion's not too bad, and deletion is going to be is going to be pretty hairy. Find, fortunately, is going to be like most tree algorithms, really, really simple. The other thing that we need to notice is that with inserting this stuff is that we're always in order as well. So one of the bonuses of using a B+ tree is that if we end up, let's say we want to implement search or select a range of keys, that's why we have this linked list at the bottom of the leaves, and they go left to right. So if we hold that invariant as well, then depending on how we implement the actual backing store, where we're going to store the values. This is a good tool. I like this. I should have found this earlier. All right, insert 8. We had to split the parent. Or we could slow that down a little bit, but apparently with this animation speed. But all right. Boom, boom. Too many. Hit the invariant. Recursively following up. Don't have to split that one yet. But if I insert another big value on there again, it's going to do a double split. Boop, boop. Oh, sorry, the parent's it's gonna do a double split after this one. Well, actually, no, it'll take a while to do a double split because this is going to be pretty sparse before we end up there. Even at a degree 3, we can end up with a lot of child nodes. All right. Cool, cool, cool. All right. Yeah, so deletion's probably going to be pretty tricky. Lower keys, upper keys, maybe. Yeah. Oh, shoot. No, I added the wrong one, didn't I? Pop, 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 pop. Oh, that was right. Values, right values. Yeah, it's split out there. All right, so we're just going to call lower keys. Oh, left keys, sorry. Left, lower value, lower keys. Lower values. Upper values. We just have one more. This should be just to get that all good. Cool. Cool, 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 cool. Okay. Now, lower half is now lower half, right? We're only going to keep one key in the node when we do this split. And that's going to be, I think, the head of the upper values. That friend, when we do the split, this friend here. So yeah, that'll be I think the head of upper values. Whatever the head of that is. So that is going to be the vector head. Which you won't like that much because you want that to be a vector. What's that function that just is it singleton? Just to create a vector from a single value. And this one, what are you up to here? What are you up to? Ooh, you couldn't do K. That's not upper values, it's upper keys. Right, remove the key, not the value. See, this is actually why Haskell's so good and why I love it. Right, I could have made that mistake easily in another programming language and not noticed until I ran the tests or whatever. But I get that feedback loop super fast here. I love it. Okay. So this list here is just going to be the lower keys, and which we colloquially called left and right, so that's still technically correct. We could probably have still kept the left and rights thing. I don't know if this makes it any more or less understandable. Because we're just changing the name of things. For the most part, we've only really added this one here. Hopefully it aids our understanding, though. Cool. So we still have to talk about insert into at some point. Get rid of lower half. And then we have to take the else case. Or we're going to insert onto the right-hand side. Okay, cool. I think inserting the right-hand side is going to look fairly similar to this. Right? So I don't need that to do anymore. We took care of that. And I can't imagine it's going to be, the equation is going to be terribly different. So let's just assume I'm right and just make it insert onto the right. And then maybe we can write some tests to assure us that we're on the right path. Okay, so insert into not the lower values, but the upper values. So that'll be upper keys prime, upper values prime. So this is lower keys. This will be up key prime, oh, values prime. And that should still be true, regardless of which side of this case we're on, I think. And then we just have to fill in insert into. So what do we need from insert into here is we just need to make sure that it preserves the order. Right, so I noticed that whenever we inserted a value that was, say, greater than, it always insert and it created a new leaf node here. It's always in the correct order. So we could be pretty inefficient at this and just cons it into our vector and sort it. Just to know that it works. Right? And then we can make it faster later. I think that's a pretty good approach a lot of the time. But again, not 100% sure about that. Although I'm starting to feel better, folks. Actually, when I first started this stream, I don't know if anybody was tuning in for that, but I was kind of going, because I've been having kind of I don't know if you have these days, but I have these days where I'm just like, I don't know what I'm doing. I'm a terrible programmer. There's so many people out there that are way smarter than me. They know a lot more things about Haskell than I'll ever know. And usually I'm okay with that, but sometimes it takes away my motivation. You gotta like confront it. But now that I'm getting into it, Haskell always makes me feel better. Once I'm programming, I'm like, I'm good. Good to go. It's when I'm not programming, I'm like, oh, I wish I was programming. Anyway, so yeah, insert into. Let's be super hacky with that for now. This is, what do we think it has? Sometimes I forget to write in the types, and I really should, just to remind myself. I think this is just going to take some vector of A. And it turns out vector of A. But it just maintains that sort property. So let's put that X on there. That's, what is it, vector to via cons? Cons, yeah. And then we need to do one more thing with that. Do we have a sort? Uh-oh, vector doesn't have a sort built in. Oh no. What am I going to do? To Hoogle. I should get some sound effects for the stream. That would be fun. Little Batman. Sort. No, I want sort with a vector. Can it do that? No? Yeah. Let's try. Let's put the ORD constraint in there. So maybe that's what the signature would look like. Yeah, No, no, no. Ah. Okay, we could be super cheeso. Make it a list. Convert it. Just so that we can sort it and then convert it to a vector. I can't. I guess I can believe it doesn't have a sort. I guess. Not too happy about that. Nope, sorry. It's going to take an A. It's still going to be the same type. We're just going to do this internally. Nobody has to know. Ugh. Ugh. Okay, so we can't really do this totally point free because we're going to have to transform our vector. All right, so we're going to have to... Well, hopefully we have something like that. To list x's. Yes. We're going to sort that. Oh, no, we're going to cons onto that list, x. It's going to complain at me about something, so I'm not being very smart. No, okay, just not catching up yet. So we have a list. We got to return a list of A and return a vector A. So we'll do the V. We'll do the sort here. What does sort need? It needs a constraint, of course. Now you happy? What? Oh, probably in data.list. Yeah. And then v.from list. Ugh. Ugh. Real life streaming, folks, you can't hide it. Can't hide it. Live coding is real. This is what programming is. It's all trade-offs. Okay, what did we get wrong with this type though? Right. K. What's the type of K? K is just a K. Yeah, I'm mixing up types here. The function insert2 is applied to 4 arguments, but its type only has 2. That's our problem here. That would be a problem. Thanks again, Haskell. So yes, we're expecting a tuple here. That's what I was when I originally wrote this. I thought, yeah, I'll hit 2 birds with 1 stone and return a tuple. We could still do that. Or we could just create the extra binds. It's not that hard to do either. Yeah. Uppercase. Upper values. Pop, shove it, good, bang. It compiles, therefore it must work. Probably not, but maybe. It has happened to me a lot more than I care to admit. You know, when people say, like, mistakenly, that, you know, if it compiles in Haskell, it probably works. Or it works. Well, usually doesn't, but sometimes it does, and it's like, hey. All right, so let's reload. Yeah, we still have the otherwise in that formula there. I don't really care. I just want to test this out. Can we ignore that? No, I won't load without it. Just comment it out. I'll put it back, I swear. Cool. All right. Let's let our leaf be one of the things I really hope the language Haskell server can do. Language Haskell server. You know what I mean. The language server for Haskell that's like super slick now and getting better is to steal the idea from Dante where you can have like inline code examples that you can just send to GHCI and have it evaluated in the buffer. Love that. Love it. If it's not in a feature request, let's make that feature request. And then maybe we'll implement it. I don't know. I'm really liking the way GHCID is going. So, yeah. Leaf. Here's our definition of leaf. Let's construct one. It's got an order. Let's start with a small one, like we did in our visual example there. An order 3 leaf. Oh, we don't. We got to import vector because we're going to need to. Okay. Sorry. Let leaf. Going to use leaf as an order of 3. We're going to do an empty vector there for the keys and the values, and no sibling yet. It doesn't have a constructor for that because, what did I do wrong? Oh, I'm probably in the wrong place for that. Let's get back into this Rosby server. Yes. Yes, there is. All right, because then you don't have this tired old process of hopping over to a terminal and stuff. And I really like that about Dante. I really liked. So I used to use intro in Emacs as well, which was really sweet before this IDE business took off with language server. And you could pull up your REPL right in the buffer with your modules all preloaded. It was pretty dope as well. Sadly, intro, rest in peace. Right, so we're going to import that again. Qualify, please. And do I have leaf and scope here? Yeah. Cool. So we're going to let our leaf or 3, please. Vector.empty And no pointer. Okay, there's our leaf. Happy little leaf. Actually, maybe we don't want that to be empty. Let's just say it has some keys in it. We don't really care about the values, so I don't care. This is a wonky, talky, honky, donkey vector. It's from this weird kid's book called The Winking Donkey or something. It's really strange. I'm not really sure what to make of it. But it tries to rhyme everything with donkey, which you kind of have to go stretch pretty far to do. Okay, so we're at order 3. So if we go to insert a key here, we should be calling split leaf. And hopefully, what do we expect to get here? Right, so something that calls this function knows that we have to split. So it's already taken care of the invariant about checking if we're at the right thing. So when I do call this though, we're gonna, depends on I guess what value we're gonna pass in for k and v. But if we choose lower, it should, let's do that one first. Let's put leaf in. So if we choose a k, say 1, that should insert on the lower side of our split. So we should get a node with 2 children, a leaf and a leaf, with 1 and 2 in it, and then 4, 6 in the upper, and then 4 should be the key, hopefully in our node if we, I think that's right. So let's go that, leaf with a key of 1. We don't really know what the values are. So hopefully this will work and not give me a type error. And Bob's your uncle. Nope, it did. Okay. So we did get a node, of course. That was expected. The node keys is 6 though. Okay. So that's probably not right. And the node children. So let's just format that better so you can see it easier, and I can read it easier as well. Let's just take this whole thing. All right, there's our node order. Node keys, node children. Let's just pull that a little bit to the left. So about 1 leaf. It's holding the whole value over and not just. Okay. That might be a problem as well. 2 leaves. Okay, that's our node children, whatever. Okay. Oh yeah, it's taking a whole copy of the other leaf in our just, so meh. However, we do have one, 2, and 4 here. And on the other side, we have just 6. So I think our split is probably not right in the equation there, where we're splitting at. We looked at that pretty hard though, and I thought that was quite right. Because we do the split first and then we're inserting. So we're splitting 2, 4 to the lower bound. All right, because we took the midpoint to be the ceiling, so that makes sense. And then we insert the 1 on the left-hand side, keeping the order, which is good. Let's double check with our visual example. Doohickey. Oh no, did I close it? Ah, I did. No, that wasn't it. There we are, friend. Okay, so we did our thing. We had 2, 4, and 6. Oh, so we should have. Good to know. So this should have been a degree 4, but it's we're just checking the splitting right now. We're not checking the degree here. Yeah, so the 4 and the 6 should be over here. Two is over here, and when we insert the 1, that one will go over there and be inserted just fine. Okay. So let's do that with a degree 4. 2, 4, 6. And then we insert the 1. Okay, this is where we should split, so we're calling a split function. Yeah, this is more what I was expecting here. 1 and 2, 4 and 6. But instead we got 1, 2, 4, and then 6 on the right. So I think to fix that, this bound should be floor, not ceiling. Where are we? There we are. All right. Oh wait, yeah, no, inserting 1. Okay, cool. Yeah, there we go. So we have see the keys there, 1 and 2, as expected, 4 and 6. Okay. So not perfect, but it's a start. It's something. Seems somewhat right. So we should probably, once I commit this, we'll slot it into, how much time we got? We got 20 minutes left, so we'll try and, maybe we'll try and slide it into the other case on insert and see if our insert function works, and then we'll probably have enough code that we should probably start writing some invariants and some property tests for that. All right, Checkster, sorry if I missed you, but it was good to see you in my stream. I hope you come again if you're catching this later on YouTube to catch up. Thanks for the follow, friend. I hope those follow notifications are showing up on the stream, because I totally configured that, but I don't hear the thing going off. So thanks again for the follows from fellow raids, Croptical, Eric Coates. Thank you very much. Checksor. All the follows are very appreciated. It makes me feel like I'm doing a thing here, and that we're spreading the word, the good word. The Church of Monads. Actually, let's not do religion. It's the worst. Well, not that religion's worse, because if you're religious, that's fine. But let's not start a new one, because we've got enough already. Especially when it comes to programming languages. Yeah, so let's see. We modify the B-tree file. We finished the that split leaf to try. Okay, and let's jump back over to the B tree. Okay, so the other part of this was in the insert. Oops, I left that commented when I checked it. Yeah. Uncomment region. That's okay. It's okay. We'll fix it. We haven't pushed it. Sorry. Stage that. So I'm just going to fix that quickly. Just squash the commits together and rewrite that. Maybe we'll do that at the end though. And in the meantime, we wanted to insert on the otherwise branch. So this is where we're checking and discriminating on the order of the node that we're looking at right now, which in this case is the leaf at the root, because we're looking at the B tree. One thing I was kind of thinking about that we might need to structure our insert around is that while I feel like this new type constructor was a good idea for the root, because the root of a B plus tree can be either a normal tree node or it can be a leaf, but it has its own kind of special rules. But when we're sort of traversing the internal nodes and the leaves that aren't the root, we need to treat those differently. We're doing inserts, so we might need some kind of helper function for those. So right now we're just handling the kind of the root node case here. Right, so where the keys is less than the order, we can insert into. Which I think is not quite right? If we do 3, 2, yeah, it's keys, it's order minus 1. So if we insert 4, it's going to split. Yeah, okay, that's actually fine. Yeah, so when we go to insert the third one, if our order is 3, then we will get to this otherwise branch. Okay. I don't know, I was getting tripped on that, but yeah, then we're going to split the leaf and turn into a B tree node. So we give it the leaf that we pulled out up above with the K and the V. And then we still have another wrapper we forgot to put in there, so so many wrappers. B leaf, yeah. And, no, sorry, B node. Giga. I don't have the K or the V, and that's because they are called key and value, respectively. I was looking at the type signature. Oops, and then I changed the wrong thing. It's been a day, folks. Been a day. Okay, now what am I doing here? Yeah, I gotta add the ord instance up here, which we didn't add. Cool, 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 cool. I don't know. Should we give it an insert a shot? Let's see if we get what we get in that handy dandy online tool we found. Let's try it out. Let's reload this. Okay. We need a root node. Should be empty. Moment of truth. Dun dun. All right. So let's insert 2 into R. Oh, because insert takes an order, of course. Or empty takes an order. Delaying the moment of truth. You can tell I'm terrified. I'm like making more mistakes now. No, it's fine, it's fine. Can't break computers. It's fine. Yeah, I mean, you can break computers. Just ask my kids. They've done it a lot. Right. Let our root empty order of 3. Did we call it? Did we change the name of it? And I forgot. Yeah, we called it muck order. That's right. We had that whole thing about muck. Okay. Good to know, good to know. What am I doing here? Okay, empty takes the order. Getting way ahead of myself here. Yeah, empty takes an int, not a muck order. I don't have to construct. Oh gosh. Empty 3. Come on. There we go. Whew. Okay, so we have an empty tree here that we're starting off with. Insert into root 2, some value we don't care about. Okay. So we still have a leaf, which is fine. It's exactly what we want. Now if we insert into that, 4, still have a leaf. Noticing something already. We're not maintaining the order invariant there. So we'll have to fix that. And if we insert again, 6, and we should get a split. 2, 4, 6, 6, 4, 2. So we're not getting a split. So let's see if we get a split now, though. That probably just means we just got the guard wrong. Now we got the split. So no biggie, probably just got the guard wrong, but so we got the B tree root and the node. The order is still 3, which is preserved. That's good. 4. So the second child, the head of that one should be 4. Right, 1, 6. Leaf sibling 4, 2. 4, 2. Nope. No, we got something way off here. That's okay. We can fix it from here. So I'm going to note that down, though. All right. Well, this one is easy to fix. It's order -1. And this insert business might be related to the fact that we're not preserving the order of the values inserted. In this case, we're just consing. So now we're here, might as well just fix that as well. What? Because we don't have vector sorting. Oh, it's going to be brutal. I'm sure there is a sort. Like, there's got to be. For vectors, there's got to be. Just has to be. It can't be this way. Okay. It's going to be super, super gross. Forgive me. For I will sin. I will sin. Talking about not being religious here. Yeah, sort. Oh, sorry. From list. Don't tell anybody you saw this. Just kidding. We're basically just going to do that here as well. Because the indices need to match up, which we're going to have to keep track of. Ooh, since we're going to be sorting these, yeah, that's not going to work. Okay. I just want to check the keys from this for now, but we're going to have to totally change this. This is not right at all at this point. We're in hacking Haskell territory now. Yeah. Yes, we are. Yes, we are. We are in non-exhaustive. Pattern match mode. Okay, that's fine. So the node has 4. That's hopeful. Keys is 2 on the left and 4, 6. Okay, that does seem to have fixed things. Seems to have. So I'm happy with that. So we didn't get too bad. Let's see, like, kind of knew what was going on. So this is gross, obviously. We're gonna have to come up with something for that to figure that out. But the overall formula, the overall equation, we're getting there. Works in this small case for this small bit of the insert algorithm. So we're doing it in pieces, which is actually kind of cool if you think about it. We're not having to think globally about the total algorithm. We can actually implement it in parts and reason about it in, like I've been saying, equation a lot. And then knowing that, looking at the data and going, oh yeah, it's because, you know, we didn't get the guard right for the order check and we went to the wrong branch, or you know, we got to sort those keys in this part here and that kind of stuff. So I'm kind of happy with that. Also, like when we found the midpoint part too as well. And we changed it to floor, and then it kind of matched our little model here, which is good. So I like that. I think it'll be interesting to come back to this once we finish it and take what I've learned from algebra-driven design and see if we can design B plus trees from first principles. Do we get the same results? Or do we even come up with a different way of coming up with the defining the insert algorithm and deriving it? I don't know. Anyways, this hasn't been the most algebra-driven way of designing this so far, but I think we're going to have to wrap it up there. I want to save the last few minutes just to look at the project, because some people have been messaging me about maybe like, you know, this is cool what you're doing. Can I, you know, I'm kind of new to Haskell and I'm looking for something to do. Is there any way I can contribute? And I've said a number of times that, yeah, man. Yes, friend, let's get people contributing. So if you're thinking about working on a Haskell project and you want to get your toes wet, I'm totally open to getting PRs. I have a couple of issues in the backlog here for things to work on. A couple of light things. Documentation good. Contributors guide is good. A REPL for the client would be nice. And we're working on the index right now. There's something else I was thinking that would be a nice enhancement. The logs. We're using Monad Logger right now, and it like sometimes took us a fair bit of work to get it up and running. There's a cool library I've been looking at. I don't have a strong opinion on it because I haven't used it before. But it jives with me. They're saying a lot of things that are like, when I think of logging, this is what I like. I like structured logs. So like a lot of the applications I build these days log with JSON straight out, because it's super easy to parse and it's fairly structured. So when you want to create, when you're using something like Rosby, say, and if you're going to use a key values database in your architecture, and you want to be able to sort on certain facets of what it's doing, it's great to be able to have JSON there, because a lot of things understand how to parse that and use those data structures for creating those things. So suddenly you can turn your logs basically into like a lightweight observational kind of framework. And Colog has been pushing some new features they've been talking about to do structured log. So it'd be kind of cool if somebody wants to investigate putting a Colog and taking a Monad Logger. See if that kind of helps the project and gives us better flexibility and more and structured logging output rather than stringy output. I still want to maintain, like, for debug log, and also different log levels. So like when we're doing debug logging, we can have like positional output, you know, like line number this, source file that. This debug error happened, but if we put it in production mode, the server will kind of squelch those and just output only the relevant log things there that's configured to do. So yeah, Colog is something it looks really cool. So that would be cool if anybody wants to experiment with that. So I'm going to put that one as an enhancement. We'll put the enhancement label on it. I don't know, we have an experimental label. I guess enhancements could also be experiments as well. Seems fine to me. Yeah, how do I do that? Somehow I did that with a keystroke and I'm not exactly sure. I'm trying to remember what it was. Anyways, Colog. Put Cool. So that was something I was thinking about earlier this week. It'd be nice to experiment with that. So if anybody wants to try and take that one on, that would be kind of cool too. Yeah, that's it for tonight then, I guess. So thanks again for all the follows. Really, really appreciate it. And like I said, I was talking about maybe doing something with Vlad. So if you haven't seen Vlad's stream, you should totally follow him as well. Because in addition to Haskell, he does Learning Thursdays and Podcast Sundays, and he talks about PureScript and other cool projects. So check out Vlad's stream in addition to this one. Give him a follow. But we might do something together at some point. Vlad, yeah. Oops, I'm not going to this stream. That was an accidental click. So yeah, check out Vlad, CVLADFP there. You can see that. And give him a follow. So we might do something soon. I don't know when, but I'll keep everybody posted. Thanks again for tuning in. As always, may your monads be free, may your types check, and we'll see you next time.